Okay, hello everybody. Welcome in to ME2001, also known as your favorite class, right? Yes. Okay. Uh, Going to continue our discussion of moments and cross products and etc. today. A couple of announcements. You do have a homework that is due a week from today. Yesterday, sorry. So I did post that online, so make sure to take a look at that. That's going to be on the stuff that we're talking about for this entire week. And I think after today, you probably should be able to do at least the first couple of problems on that homework. So if you want to maybe get started or try it, maybe after today, but definitely after tomorrow's lecture, you should be able to make some work here. Hope we like the meme today. A little bit funny, maybe a little sad that we no longer have Trebek as our host, but I think that's kind of funny. All right, let's pick up where we left off. Okay. So just a quick review. Yesterday we were talking about cross products and sort of introduced this new mathematical idea. Cross products are vector products. And so we motivated yesterday's lecture by discussing two vectors that happen to be in a plane, and there's an angle separating the two of them. So vector P and vector Q separated by some angle theta, which you kind of see here. We said that the cross product of these two guys will result in a vector that points out of the plane containing those two vectors, so perpendicular to the plane containing those two, and that the magnitude of that particular cross product is going to be something like the magnitude of vector P multiplied by the magnitude of vector Q multiplied by the sine of the angle between them. We also said that the resulting direction of this particular vector B depends on sort of the order in which you take your cross product, and it utilizes the right-hand rule. So we talked a little bit about the right-hand rule, but the basic idea is that you want to stick your hand in the direction of the first vector, curl your fingers towards the second vector, and the direction that your thumb points, assuming you're using your right hand, is the direction which will result for your cross product. So we went through a variety of ideas and sort of looked at all of the mechanics behind this. And we talked about when cross products would be equal to 0, and that would be if vectors are aligned on top of each other or 180 degrees for each other. So we say in the math language that that's n pi radians from each other, where n is an integer. So we saw some examples of that. We looked at other properties of the cross product, including that the cross product is not commutative, meaning P cross Q does not equal Q cross P. So that's very important. And in fact, P cross Q is negative Q cross P. So that's another important finding here. And that just has to do with, yes, they'll have the same magnitude, but their direction will be flipped because of the sort of weird, wonky right-hand rule that you've got to follow. Vector products are distributive, which is an important characteristic of vector products, and we use that a little bit later. But it's important to note that they're not associative. So we talked about all this. And these are all kind of the properties that we have for our vector products. We did an example yesterday with some very simplistic vectors, P and Q, with magnitude of 6, magnitude of 4, angle of 30 between them. And then we looked at what is the magnitude of that resultant and what is the direction. All right, so resulting in the positive y direction for this particular example, giving you a vector of 12j in this particular situation. All right, then we talked about what happens if you start taking cross products of our unit vectors. And remember, unit vectors are magnitude 1, generally pointed in the direction of your x, y, z coordinate system. And we looked at, all right, well, if each of these unit vectors is of magnitude 1, and the angles between them is either 90 degrees or 0 degrees, depending on if you're taking the unit vector or the cross product of itself, then various things result. And long story short, we kind of came up with this full gamut of all possibilities for cross products between your typical unit vectors, I cross j, I cross k, so on and so forth, all throughout, and kind of came up with, your cross product circle, this idea of you create for yourself this diagram that if you follow it in the clockwise way, you get a positive value. If you follow it in the counterclockwise way, you get negative. There's a couple of different ways that you can represent this circle. This is just one way. There are other ways that it can be drawn, so you might see it in other ways. All right. So this helps us to define, which way is positive if we're taking our cross product and which way is negative. We expanded on this idea to think about arbitrary 3D vectors in space, here P and Q, having some components in x, y, and z for both vectors. And we used our distributive property of the cross product to look at what happens if you do the cross product of these two vectors after breaking them down into their I, j, and k components. And we did that. We saw a lot of interesting things like the I cross I components would cancel. And when we had things like I cross j, our resultant would be in k. I cross k, our resultant would be in negative j, so on and so forth. So you can go through all of the math and sort of retain all of the variables associated with the vectors here and come up with a final result for two arbitrary vectors in space, p cross q, that looks something like this. And this is about where we left off yesterday. And this equation is helpful in that it tells us, all right, if I have, the y component of p multiplied by the z component of q minus blah, 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 all this is kind of the mechanics of what results when you do p cross q. And you may consider memorizing this equation, but that's impractical because you get like one little thing wrong in your memorization and things fall apart, okay? It would be much nicer if there was some easier way to remember how to do this particular cross product. And that's what I'm going to teach you right now. And specifically, there's a sort of a determinant form, or I think what Grace called yesterday, the chart form of the cross product. So I'm going to introduce that idea right now. I'll say that the equation above is useful, but sort of difficult to remember. Memorize or remember. You could probably do it. I mean, you guys are all really smart and some of you are pretty good with memorization. So I don't doubt that you could probably sort of commit this to memory and execute. But why commit it to memory if you can just have some other mnemonic or other metric that makes it easy? Okay. And I will show you one technique that you can use to execute this cross product a little bit more effectively. So given a vector p, which is pxi plus pyj plus pzk, and a vector q, which is qxi plus qyj plus qzk. You can sort of rearrange this into, I guess, what your book calls the determinant form. So we rearrange into what looks like a 3x3 square chart. Okay, and I'll show you what that sort of looks like now. So in order to sort of arrange this chart, we want to write for ourselves that P cross Q is equal to, I'm going to draw large vertical arrows here. And I'm going to have kind of like a 3x3 sort of looking matrix that I'm going to write in here. The first layer is going to get my I, J, and K unit vectors. All right. The next row is going to get the contributions of the vector P. So that would be Px and I hat, Py and J hat, and Pz and K hat. And the next row is going to get the contributions of Q. It's very important that you do not mix these up, okay? The order in which they appear is very important. P first, Q second, okay? This is important when going through the mechanics of this particular operation. And then to execute the cross product, what I'm going to do is I'm going to multiply across the diagonals in specific ways. Now, what do I mean by that? Well, if we go back up to our equation that sort of defines this particular cross product, the first term that we'll see is something like Py times Qz in the I hat, right? And if I look to this sort of like determinant form that I've made, if I look at this first diagonal across, I'll notice that Py, Qz, and I hat all kind of form across the diagonal here, right? So I would notice that if I multiplied those three guys together, that I would end up with the first term in the equation that defines this cross product. All right, so that's nice. Okay, I'm going to continue that trend with the J and the K directions. All right, so if I thought about the J direction as well, I could continue down and make my diagonal and see that I sort of like run out of space over here. So I need to wrap around and finish by hitting QX. All right, So my first term would be this first one that I've drawn here, which is py qz I hat. Then this little diagonal is sort of the second bit, which is going to be plus pz qx j hat. And then I'll continue with the last bit. Here's my k, I'll wrap around. And I'll have k hat, px, and qy. So px, qy, k hat. Okay? So those are three terms that I sort of get from my cross product. And if we go back up to our original equation that we sort of defined yesterday, that would be these three positive terms that you see. py, qz, and I hat, pz, qx, and j hat, and px, qy, and k hat. All right, so that's what we see here. And the question is, well, what about the negative terms? All right, where do the negative terms come from? Well, the negative terms comes from taking that diagonal the other direction. Right? So the negative terms are going to come from not down and to the right, but down and to the left. So here I have I hat, wrap around, pz, qy. And since I'm going down and to the left, I'm going to make a negative. So minus pz, qy, I hat. Go the other way. Keep going here. Minus px, qz, j hat. Right? And finish it off with py, qx, and k hat. Okay. And so our final result here is the same as sort of what we showed above. Okay. This is the same as what we had above here. I mean, it's rearranged slightly because I have the positive and negative terms separated below, but it's the same thing. All right. So this is one easy way to compute your cross products quickly. And I like this method. I use this method. You'll see me use this on homework. You'll see me use this on exam solutions. So I advocate for this method. So let's do a quick example right now where we actually like put in some numbers and actually calculate like what some cross products might be of some typical vectors. So this is not in your note handout, but I'm going to include this here. All right. So let's do a quick example where we look at doing some of these. Two different examples with four vectors here. Okay, you might be copying. I'm just going to copy this over to the notes really quick. So. Make this bigger. Yes, I can. Okay. So let's give this a whirl. So we've got two vectors here, P and Q. We're going to take the cross product of those two guys. So maybe I'll call this A and I'll call this B. I'm going to do these two guys separately, I guess. Okay. So let's look at A. If I want to do P cross Q, which is kind of what the problem is asking for, I'm going to look at this sort of like determinant form. So I'm going to set up my chart and I'm going to execute this sort of cross product technique that I just sort of talked about. All right. So here we have I, J, and K. And I'll sort of close my determinant form. And so I want to arrange P in the proper way. So negative 4i 2j 3k is negative 4i 2j 3k. And then for the vector Q, I have 2i and 4k, which means I have 0j. So 2i, 0j, negative 4k. All right. So I'm going to go through this and execute like these diagonal multiplication to get me through my vector product. So the first one here is 2 times negative 4 in the I hat. Okay. Keep going with my next term, which is 3 times 2 in j hat. Okay. And finally, I have negative 4 times 0 in k hat, which is just going to be plus 0. I guess I can write it here for completeness. Okay. And so those are all my like positive terms resulting from kind of like going down and to the right in this sort of determinant form. Next, I'm going to go down and to the left, and my terms will be negative. So the first one here is I, 3, and 0. So what will be negative 3 times 0 I hat. Obviously, that's going to be 0, but I'm just writing this for completeness. Next, j, negative 4, and negative 4. So we're going to have, because we're going down and to the left, a minus negative 4 times negative 4, j. And then finally for k, down and to the left, minus 2 times 2 in the k hat. All right. So this would sort of be like the fully blown algebraic form. I mean, this is kind of like beating it to death, probably too much detail here. I think most of you get the idea, but I'm just showing it for mostly for completeness. All right, so here we have a negative 8, and here we have a 0. So we'll have in total negative 8 I hat. In the j, we have positive 6 minus positive 16. So that's going to be 6 minus 16, which is negative 10. All right. And then here I have a negative 4 times 0, which obviously is 0, minus 2 times 2, so it's going to be minus 4k hat. So this would be my final answer here. All right. That's sort of how we use this determinant technique. Do one more.
Is the sign of J switch, or is that for like if you do a different method?
So the question is, does the sign of J switch? I'm not sure what you mean here. So when I'm going down and to the right, I generally have plus signs in front of my terms. You see that?
Yeah.
And then when I'm going down and to the left, I generally have minus signs. So here's a minus sign, minus sign, minus sign. So if I think about what's happening in the J term, I have plus 6, and here I would be plus 16 inside the parentheses, but I have a minus in front. Okay, so my total J contribution is plus 6 minus plus 16, which is negative 10. Okay, let's continue. All right, let's go for one more. And we'll look at this guy here. And this guy is a little bit awkward and a little bit weird, but we'll see what happens with this guy in the end. All right. So 1, 3, negative 2 for P. So let's construct here. So we have 1, 3, negative 2 for P. And we go back up. And for Q, we have negative 2, negative 6, 4. All right. So we can go through this again. I'll go a little bit quicker this time and do the multiplication in my head. So here I have 12i. Here I will have positive 4j. Here I will have minus 6k. And now going down to the left, I have negative contributions. So negative 2 times negative 6 is positive 12. But since I'm doing the down and to the left portion of the cross product, this will be minus 12 I hat. Here we have j times 1 times 4 is 4, but I'm going down and to the left, so minus 4 j hat. Okay. I have minus 2 times 3, but it's down to the left, so I got to flip the sign, plus 6 k hat. Put this all together, we see everything cancels out here. Interesting. So this is the zero vector. That's how you would represent the zero vector. Now, why is this, right? Our vectors are not equal to 0. Their general magnitudes are not 0. What would this actually look like if we tried to plot this in like three-dimensional space? Trying to think about why this particular cross product is 0. Okay, so if I thought about, representing each of these vectors in like an x, y, z coordinate system. Let's think about just drawing this vector p. All right, so it's 1 in I, 3 in j, minus 2 in k. All right, so 1 in I, 3 in j, minus 2 in k. So that guy's somewhere down out here. All right, it's a decent representation of that particular vector. All right, so what about q? Q minus 2 in I, so that's somewhere back here in space. Minus 6 in j, so that's sort of way back here. And plus 4 in k, so that's up here somewhere. So that's going to be something that looks like that. All right, so here's your q. And here's your p. So it's not obvious upon immediate viewing with those general components of p and q, but the angle in this particular situation between vector p and vector q is 180 degrees. So if we remember that the magnitude of our cross product is equal to the magnitude of p times the magnitude of q multiplied by the sine of the angle between them, in this case 180 degrees, we'll note that sine of 180 is 0, and that's why I end up with the 0 vector. Right? So just because you have a bunch of numbers or a bunch of things going on with your cross product, you could still end up with a 0 even if you're doing everything correctly. So don't be so concerned if that's what happens. You just gotta let the math take you there, as I like to say. Okay. So there you go. There's a quick jaunt on vector products, cross products, and how to execute in 3 dimensions. Now, why do we care? All right. Why do we have this tool and this technique now? Well, remember I told you that we had to introduce this technique of cross products and vector products so that we could actually discuss the math behind moments. Now, if we remember our moment conversation, the idea of a moment is it's like a twisting force, right? And it's somehow related to the amount of force that you apply and the distance that that force is away from the point of application, okay? So now let's finally give what the mathematical definition of a moment is. So here's the moment of a force. We're finally there. It took a little preamble, but we're getting there. All right, so let's write it in words first, and then I'll give you the math. The moment of a force, which I'll label as capital M with a bar over it. Moment is a vector. All right. Of a force. Here I'll label it as a force vector. Seems a little redundant. The moment of a force m of a force F. Maybe we should do the moment m of a force F. That's a little bit better, probably. It's the Department of Redundancy Department. Okay. All right. The moment m of a force F about a point O in space is the cross product of the distance between O and the application of the force and the force. Okay, so the distance between O and the application of the force, that's one vector. That's your position vector that locates the force and the force. So if we put this in mathematical language, the moment about some point O is the position vector R crossed with the force. Now let's maybe show what that is sort of pictorially. Okay, so here we are with X, Y, Z. And here we are with our coordinate system, and let's say it's centered at O. Let's say we have a point that's out in space, and here that point is point A. And let's say that there's a force that occurs at that particular location A. I'm just going to draw it in an arbitrary direction. And let's say that this is the force at A. Then the moment of this force about O is the cross product of the distance between A and O and the force at A. So we need a position vector here that locates point A, which is where the force is applied, and that is the position vector R. Now, I like to be very specific with my position vectors, and I like to give the position vector some sort of, subscript so that you know exactly what the position vector is defining. And the way that I like to do that is I like to say the position vector arriving at blank from blank. And the way that I draw that is something like the position vector R arriving at A from O. All right, that's how I give my nomenclature. So with that idea, we can maybe give a little bit more reflection of this equation a little bit more clearly. The moment about O is the position vector, which arrives at A from O, crossed with the force that exists at A. That is your moment. Oh, had a little drunken line there for a second. Okay. So if we're trying to picture what this moment would look like on this particular diagram, well, here we have this position vector that's locating A from O. That's what A/O means, the position vector locating A from O. And we have this force at A. So if we thought about like what the cross product of this would look like, well, we have like the plane that contains A and O. Let's say that that plane is here, something that looks like that. And remember that our cross product is perpendicular to the plane that contains those two vectors. So if I thought about my right-hand rule and thinking about where the moment would occur from this R cross F, I would have, sticking my arm in the direction of R and curling my fingers in the direction of F. My thumb is going to point out from O in the direction of the resulting moment. And so the resulting moment, let's do it in green here, is going to look something coming off of the plane like this. So here's your resulting moment about point O. Moments usually denoted with a double arrow. so that you know it's like this twisting effect. And when I think about if I had some force A and if I had some position vector, what sort of torque would I produce with that force about that point O? So think about like your lug nut sort of idea. That force being like the force you apply with your hand, and the position vector R being like the distance you are away from the lug nut, right? So if I thought about what torque that's giving me, it's generating what is like this spin, about this particular axis. So it's trying to sort of like torque about that particular axis. And remember when I first introduced moments, we said that we could sort of show moments on our free body diagrams or show moments in space using either like this rotating arrow, this curved arrow to sort of indicate sort of the direction that you're twisting, or we could use the double arrow, which is like the axis of rotation. That would be like your thumb in the right-hand rule as you're sort of like curling your fingers around R cross F, right? That's the general idea there, okay? So my moment here is the position vector R crossed with the force at A. And you guys already know how to do all of this, all right? We've set up in the past position vectors between 2 points. We did this with like, what is the unit vector that exists between 2 points in space? How can you define that position vector? We've done that before. You know how to define a force in 3 dimensions by resolving it into its various components. And now you know how to do the cross product, okay? So you can do this. The lesson could be over now and I could tell you to go do your homework and you should be able to basically do it at this point, right? So let's make a couple of final notes about this particular idea. The moment is perpendicular to the plane containing R and F. Okay, obviously. The magnitude of the moment is the magnitude of the position vector multiplied by the magnitude of the force multiplied by the sine of the angle between them. Right. The direction follows the right-hand rule. Okay, I'm going to pull up a slide here that has some examples of just like moments in action in real world that you've probably seen before. Okay, and so here's our general equation and some sort of real life examples. So here's your moment equation, right? The moment is the moment arm. Sometimes the position vector we sometimes call the moment arm is R cross the force, which is F. All right, and they have some nice examples here of like how you might increase or decrease the magnitude of the moment given varying forces or varying moment arms. And so I like the comparison here with like this girl that's blowing on a pinwheel. Obviously she can't produce as much force as like the gale force of the Midwestern winds on a windmill, right? So this is a difference in just like the amount of force that you can apply that would amplify this particular portion of the term, right? This example with the wrench gives an idea of something that you've probably seen before if you've ever done any like handiwork with a wrench, be it large or small. This is an example of a guy sort of like turning a wrench on a radiator that's got a relatively small moment arm, only a couple inches here. versus the guy who's working on this railroad tie that has a moment arm on this particular wrench that's like, 3 feet, looks like 2.5 feet or something like that, okay? So this is an example of increasing your distance to the application of the force. So here he's applying his force this direction, and the distance to that particular point, which would like be point O in this situation, is very, very large compared to this situation, where your distance from the point of application here is relatively short. All right, so that's sort of the difference that we could potentially see. Okay. Those are some moments for you. I like teaching moments because, and not teaching moments like the moment that we're having right now for teaching, but teaching the engineering term of moment, because I think people get a general idea for what a moment is relatively quickly. It's like this twisting force, even though maybe you've never like had a word for describing it other than like a torque or something, So putting a word to it and putting like this cross product to it, when you learn about what a cross product is, it sort of like clicks and makes sense. At least that's how I sort of think about it and like to think about moments. When I after I learned what a moment was, my turning of a door handle was never the same. Okay. All right. Now let's talk about calculation of moments in your typical rectangular coordinate system. Okay, baby. Now let's go back to that picture that we just had a second ago, where we had this coordinate system that existed here. That was like, I want to stay consistent with your notes, so I'll do X, Y, Z here. I think I drew it a little bit different last time, but you get the idea. And then there's going to be some, let's say, point that exists out in space here. That is point A. And there's some force that's acting at A. Let's call this FA, right? Well, we have our position vector that arrives at A from O. Remember, that looks something like this. And remember how we label this? The position vector arriving at A from O. And if we want to think about our moment about O, that is the position vector arriving at A from O, crossed with my force at A. That's our broadest definition. Yes? Okay. I know that I can break each of these down into rectangular components. Okay. Specifically, I could say that like RAO, and let's just say is Rx in the I hat plus RY J hat plus RZ K hat. Okay, that's somewhat intuitive. If I wanted to look on my graph that I sort of just made at the right here, I could sort of like project this down, project this across, project this here. And you could say that like, okay, well, here's your like Rx component, okay? Here's your Ry component. And here's your RZ component. All right, the portions of the position vector in your rectangular coordinates. All right, it's pretty obvious and easy to sort of intuit. All right. Now we can also do the same with the force vector. My force at A is something like FAX. Get your facts straight. I hat plus FAY J hat plus force at A Z K hat, right? Can resolve that particular force into its rectangular components. So again, if we thought about that, maybe here's our guy here, and this is, I don't know, being resolved in this way. All right, or here this is. These general components of this particular guy, or here this would be like FAX. Here this is FAY and FAZ. All right, so resolving that force into its various components. Right. Then we can use sort of the techniques that we just learned to execute the cross product. Your moment is RAO crossed with FA, which is this strange like determinant form that we just talked about. Something that looks like this. Make sure you're getting them in the right order. Do not do F cross R or I will scream. All right, R cross F every time. All right, and you could go through this with all of your, you know, diagonals and et cetera, and come up with your expression for the various components of your resulting moment vector, which would be something like Ry Fz minus, I wrote Fx, God, minus Rz Fy in the I hat, plus, here we have Rz Fx minus Rx Fz, the j hat, plus Rx Fy minus Ry Fx k hat. And this would sort of be like the most general expansion of the moment equation of rectangular coordinates. Okay. You are now armed to do problems number 1 for sure, and probably problem number 2. Okay. Let's see if we can squeeze in one example quick before we go. Bam. $800 Newton force exerted on this particular bracket. Determine the moment of the force about B. Let's roll, baby. So in essence, sort of what we're asking here is how much torque is this 800 Newton force giving me about this particular point B? How much is it torquing that particular point? All right. Well, let's use our traditional XYZ coordinate system here, or since we're in 2 dimensions, XY coordinate system. And we know that the moment at B is the position vector arriving at A from B crossed with the force that exists at A. It's our general equation. All right. I then will need a position vector which arrives at A from B. It's very important that you do it in this proper order. That is this position vector here. Position vector that arrives at A from B. So let's break each one of these down. We sort of have to go backwards 200 in the I direction, so negative 200I. And we've got to go up 160 in J. So it'll be minus 200 I hat plus 160 J hat millimeters. All right, continuing. My force at A. Here I'm given this magnitude, which is 800 newtons, and I can resolve it into x and y through the cosine and the sine of 60 degrees. So here I have 800 newtons times what is cosine 60 I hat plus sine 60 J hat. If you kind of work your trig here and figure these out, you'll get here that the force at A is something like 400 I hat plus 693 J hat newtons. And so now you're ready to execute your moment with these two pieces. So the moment about B is going to be your RAB crossed with the F at A. And I can set up my determinant form. I'm going to include all three I, J, and K, just so it's clear here what's happening in my individual components here. All right. So I have negative 200 I hat. I have 160 J hat. And I have 0 K hat for my position vector. A lot of times it helps to put the units on the back end of the sort of determinant form here. And then my force at A is 400, 693, 0 newtons. Okay. So we're going to have something like, if I do my first bit, okay, I'm not going to get anything from that because I have a multiplication by 0. I'm not going to get anything from this because, again, I have a multiplication by 0. But I will get something from the K hat term that's here. I'm going to convert to meters on the fly here. So my moment at B, first term that I'm going to have, which is a positive term, I'm kind of going down and to the right on my determinant form here. And again, like I said, I'm going to kind of convert to meters on the fly here. Negative 0.2 meters. That's here. Multiplied by 693 newtons in the K hat. All right. Now I'll sort of account for my negative terms in my determinant form, which is sort of this down and to the left. So here I have I 0, 693. All right, again, I'm running into a 0 there, so I'm not going to get any contribution in I. J, negative 200, wrap around to the 0. Okay, again, I get no contribution in J because I have a multiply by 0. But here now, K, I will have some negative contribution. So it's going to be something like minus, again, I'll convert to meters on the fly, 0.16 meters multiplied by 400 newtons in K hat. So my result after working through all of this is going to be negative 203, 202.6. k hat Newton meters. So it's interesting to note about this two-dimensional problem is we had both the position vector and the force vector in like the XY plane, right? So what we know about cross products is that a cross product, the result will always be in a axis that's perpendicular to the plane containing the position vector and the force vector. So for our moment to only have a result in the out of plane direction, which is out of the plane containing both the position vector and the force vector, this makes sense, right? So that's it for today. Our moment here, negative 202.6, that's the amount of torque that we're providing at B from that force. That's it for today. Thanks for coming, and we'll continue with this tomorrow.